Hello everyone, I am Ehsan and today I am going to talk about submodular maximization through barrier functions. This is a joint work with Badanidiyuru, Karbasi, myself and Vondrak. In this paper, we consider a discrete optimization problem where the goal is to maximize a function f over a ground set of items v subject to a set of constraints I. This constraint could be in the form of a cardinality constraint, a knapsack constraint, a matroid constraint, or many other types of constraints. Without any further assumption on the structure of function f, there is no hope to solve this problem efficiently. In this paper, we consider submodularity as a natural and quite useful structural property. Submodular functions formalize the intuitive diminishing returns property. Submodularity allows optimization tractability, while this property appears in many machine learning applications too. More formally, a function f is submodular if for all sets A and B, where A is a subset of B, the marginal gain of adding a new element S to set A is at least equal to the marginal gain of adding that element to set B. The submodular function f is monotone if by adding new elements to a set A, its utility only could increase. Our primary goal is to maximize a monotone submodular function subject to combination of a k-matroid and L-knapsack constraints. This problem has applications in recommendation systems, data summarization, and many other tasks. We want to show how discrete barrier functions manifest themselves in constraint submodular maximization. Our approach lies in between fast thresholding algorithms with suboptimal approximation ratios and slower algorithms that use continuous greedy and rounding methods. By using a novel technique inspired by barrier functions in continuous optimization, we propose two algorithms for maximizing a monotone submodular function such that improve the running time for a constraint submodular maximization and also provide state-of-the-art guarantees. Let's first briefly define the constraint we consider in this paper. A matroid is an independent set system over ground set N, where for any two independent sets A and B such that size of A is smaller than B, then there exists an element in B set minus A such that the union of that element with A is still an independent set. Given k matroids over ground set N, the intersection of these k matroids is simply the intersection of the independent set in all these k matroids. K matroid is a generalization of k matroids where you can find the definition in the main paper. And finally, a knapsack constraint is defined by a cost vector C over the ground set N of items, where the cost of a set S is simply the sum of the cost of each one of those elements. A set S satisfies the knapsack constraint C with a budget of capital C if the cost of that set is at most C. To solve our optimization problem, instead of making the space of feasible swaps huge and more complicated, we incorporate the knapsack constraints into a potential function. This function imposes an increasingly large cost on a feasible point as it approaches the boundary of the feasible region for the knapsack constraints. For this reason, we define the potential function for a set S as the ratio between opt minus k plus 1 times the utility of set S over 1 minus the knapsack cost of the elements in set S, where opt is the optimum value for the problem. Since we don't know the value of opt, we can replace it by omega, which could be estimated through some standard enumerating techniques. This potential function is designed in a way such that either the current solution respects all the knapsack constraints, or if the solution violates any of the knapsack constraints, we can guarantee that the object value is already sufficiently large. We also quantify the effect of each element on the potential function as a notion of their individual energy, which you can find here as defined by delta of S and A. This value intuitively measures how an element increases the utility given the knapsack cost of that element. It has also this nice property that such that if we remove elements with a negative delta, then it would not increase the potential for a set S. The main goal of our first proposed algorithm, barrier greedy, is to efficiently minimize the potential function we have defined in several consecutive sequential rounds. Barrier greedy starts with an empty set S and performs two main steps for at most r log of 1 over epsilon iterations, or till it reaches a solution S such that the utility of set S is at least 1 minus epsilon times omega divided by k plus 1. In the first step, barrier greedy finds an element B such that its addition to set S and removal of a corresponding set of elements from S in order to keep set S feasible decrease the potential function by a large margin. In the second step, it removes all elements from set S with a non-positive delta. Our algorithm for minimizing the potential function, barrier greedy, finds a feasible solution with a good objective value mainly for two reasons. If the first condition is satisfied, which means it continues the process for r log of 1 over epsilon iterations, we prove that the potential function would be very close to 0, which consequently enables us to guarantee the performance for this case. If the second condition is satisfied, which is equivalent to the case f of s is larger than 1 minus epsilon omega divided by k plus 1. Assume B is the last added element to set S. We can prove that one of the two sets S set minus B or B are feasible, and the utility of that feasible set is at least 1 minus epsilon omega divided by 2 times k plus 1. Now we are ready to present the theoretical guarantees of our proposed solutions. Our first algorithm, barrier greedy, provides a 2 times k plus 1 plus epsilon approximation. By using an enumeration technique, we can improve the performance of barrier greedy. Indeed, barrier greedy plus plus provides a k plus 1 plus epsilon approximation. This two-factor improvement is achieved by increasing the computational cost by a factor of n squared. The main purpose of barrier greedy plus plus is to provide a tighter approximation guarantee at the expense of a higher computational cost. Indeed, there is a trade-off between the quality of the solution we desire to obtain, higher for barrier greedy plus plus, and the time we are willing to spend, faster for barrier greedy. In this paper, we also demonstrate the practical effectiveness of our algorithms over several real-world machine learning applications. These applications include a movie recommendation system, summarization tags for YouTube videos, Twitter feeds of news agencies, and Yelp business locations. We also consider a set cover problem. We compared the performance of our proposed algorithms with several baselines, including vanilla greedy, density greedy, and to state-of-the-art algorithms FAST and Phantom. In this slide, we compare the algorithms over a Yelp location summarization task where there is a limit on the size of the summary, number of locations from each city, and distances to several points of interest in each city. From these plots, we observe that barrier greedy shows the best performance with a moderate computational cost. At the end, I would like to thank you for your attention, and please send an email to ehsankazemi@google.com if you have any question.